code is to track your presence in the room for the coronavirus, right? So you have to scan it. Okay, now let's see how we can take the temperature measurements with a thermocouple by using a thermocouple. Okay, the reference configuration is the one that you already saw before. So we have one material there, then we got a second material that we use to measure the output tension, for example. We got the hot and the cold junction, remember? So we consider here the T reference, the cold one equal, for example, 24 Celsius. And then we would like to know the unknown temperature at the hot junction by assuming that the output tension here is 3.59 millivolts. Okay, and this is the type J-type junction. Of course, you have to know that. So how can we proceed in order to refer to measure or to estimate the temperature? So the first thing that you need to know is that we can have a large number of cold temperatures, okay? That is the temperature of the cold junction. And also we can have a very large number of thermocouple types. So it will be very, very difficult for us to have a handy way to measure the temperature because you have too many unknowns. The cold temperature, the thermocouple type in terms of couple of materials, that could make the measurement impossible. So what is done is using the previous laws, okay, specifically the intermediate temperature laws, okay. So what we got is that we have to refer to a well-defined reference temperature, okay, when using your thermocouple, whatever will be the cold temperature, okay. So generally, we are using just a very few tables or data that are in a sort of computer program that could be very, very easily used by the transducer itself. So we refer to the standard potential that is evaluated at 0 degrees Celsius. Okay, so what you have to do as a first step is to reduce the output tension to the 0 degree Celsius standard potential. Okay, so everything will be referred to that. Okay, why that? Because you need to have just one table to remember or to memorize in your whatever computer program. Okay, one table for one thermocouple type. Okay, so just to show you how we can do, I can do the measurement. So first step is reduce the output potential to the 0 degrees Celsius standard potential. Okay, how can we do that? For example, as I said before, using tables, okay, or something that has been previously memorized in your program. And the tables are, for example, of these shapes. So we made temperature. Here I got the values in Fahrenheit. And then we can refer, for example, to different thermocouple types. I got J type and I got, for example, K type, just to give you a touch of what are these potentials. And so we have, for example, negative 100, 0, 100, 200, 300, and 400. And the standard potential of that is reported in these cells. So negative 3.49, negative 0.89, 1.94.
Is there a reason why this table is in Fahrenheit?
I can barely hear you. Is there a reason
why
why?
this table is in Fahrenheit and our
Oh,
other?
no. Just because I copied that one.
Okay.
Okay. 4.91, 794, 11.03. Or I can answer that in order to let you feel a little bit more at home. But of course, that is not the right answer.
It works for me.
0, 670, 1.517, 3967, 6.647, and 9.526. Okay, these are the standard potentials, okay, of these two type of thermocouples, J type and K type, for which the cold junction is a 0 degree Celsius, oh, okay, 32 in this case, okay, Fahrenheit, and the hot temperature is at the different temperatures that I report in the table. Corresponding to that, the output potential, so the standard potential is, for example, J-type, negative 3.49 millivolts, okay? I can add that here just to be sure. Okay, and so far and so on, so negative 0.89 and so on. Now, let me go to the end and then you can see the final. Okay, now by now just let you know that this table is referring to the standard potential, so it is the potential of the thermocouple for which one junction, the cold one, is at 0 degrees Celsius and the other one is at the temperature that I reported here. Okay, then if you are now at 24 degrees, okay, from the practical point of view, now let's go back to our example. Because the reference temperature, okay, is at 24 degrees, that is approximately equal to 75.2 Fahrenheit, okay, by using that table, you know that the output tension with respect to the 0 will be about, let's say, 75. So we are about here. Okay, it is equal to 1.22 millivolts. Okay. This information could be obtained by using the table. Okay, I don't have all the entries, but believe me that it is the output. Okay, so when referring to the same thermocouple in which the cold junction is at 0 degrees and the hot junction is at 24 degrees, then the output tension is 1.22. That is the potential standard of that thermocouple. Okay. Then what we have to do is apply the law of the intermediate temperature. Okay. That is telling me that the overall output tension is the sum of the different output tensions. We're referring to the thermocouple at different temperature. Now, I figure out that the actual temperature is placed at the 0, 24 degrees. Now, what I got here from the example is the same thermocouple is 24 and the unknown temperature. So the overall output tension will be equal to the sum of these two, the one at a measure, 3.59, and the one corresponding to the potential standard, 1.22. Okay, so let me write the second step. Second step is that the total potential with respect to the 0 degree, okay, temperature, let me call that ET, total potential, is given me by the potential at 24 degrees starting point, okay, with respect to 0, plus the one that I measure, that I call EU, okay, that is 1.22 millivolts plus 3.59 millivolts. Okay, that is the output tension is 4.81 millivolts. Okay, now what? First step, remember, second step is telling me what is the total potential that we can have by putting the same thermocouple with the cold temperature at 0 degrees and the output temperature at the one that is the unknown one. Okay, just by adding up all the two potentials that we consider. Okay, 24 and the one that we measure. The third step is estimate the unknown temperature from table, for example, for which the input is ET equal to 4.81 millivolts. Okay, if you go back to the table, we got 480 and something, so you are here, and you are having that potential equal to 4.81 millivolt, corresponding to a temperature of about 92 degrees Celsius. That is not Fahrenheit in this case. Okay. Remember, the table is reported in Fahrenheit to let things a little bit more complicated from your point of view, but the working principle is this one. I just repeat it. Okay, I got my J-type thermocouple, and I know that the thermocouple is having the cold junction at one temperature, for example, 24 degrees. Then I would like to estimate the hot junction temperature that is unknown. What I'm measuring in order to do that is the output tension of the thermocouple that is equal to, for example, 3.59 millivolts. How can I estimate my unknown temperature? In order to do that, you have to refer to tables that are all referred to the standard potential, 0 degree. So you have to refer to that thermocouple that is operating with the cold junction at 0 degree. How can you do that? First, let's reduce the output tension to the 0 degree first. Okay. Remember the law of intermediate material temperature. Okay. So let's figure out what happens to that thermocouple if the hot junction is at 24 degrees and the cold junction is at 0 degrees Celsius. Simply just go to the table and see what are the standard potentials. Okay, for that kind of thermocouple, so I have to look at the J-type column and see what is the output tension corresponding to the 24 degrees. That is, in our analysis, about 75.2 Fahrenheit. Okay, so the input on the table will be the temperature, the output of the table will be the potential standard. We can see that that potential standard is equal to 1.22. Then, law of the intermediate temperature, I sum up all these two potentials. So the overall potential of that thermocouple that is having the cold temperature at 0 degree and the hot temperature at the unknown temperature is the sum of the two output potential. So E24 plus EU, what I call that. Okay. The resulting now is the output tension of 4.81 millivolts. Last step, the third one, is the estimate of the temperature. So I go back to the table, but now my entry, my input is the tension, the output tension, that is 4.81 millivolts. So I have to enter to the right column, that is J-type column, check what is the output tension equal to 4.81 and see the corresponding temperature. In our analysis, the corresponding temperature will be 92 degrees. Okay, as I wrote there. Okay, so from the table, the corresponding temperature is 92 degrees Celsius. And we solve the problem. Please know that this procedure is the best one because you don't know, you really don't care about the actual cold temperature. It could be 24, as we had here in our example. It could be 30, it could be 50, it could be whatever. As long as my table that could be easily computerized in my database, could be whatever, is facing with that kind of temperature ranges. Okay? So this hard work is just done once in life from my friends in the physics department. I'll pay a lot for that table to my best friends, for example, a very nice dinner at a very nice restaurant. Okay, and once I got the table, I'm a rich man because I can sell this thermocouple with a very high precision. Okay, because from the sensitivity point of view, we have microvolts per degree. Here we have millivolts. So the sensitivity and the values are telling me that the temperature measurement made by this thermocouple is very accurate measurement. Okay, and we don't need anything else, just a voltmeter, because what we need is the measurement of the output tension. Okay. Yeah, much better. Yeah. Okay. So that is the general principle, okay, of the of measuring the temperature using thermocouple. Now let's see what we can do if we would like, for example, to increase the sensitivity of the thermocouple. Okay, now let's see one example. That is, for example, we have a wall temperature, let's say T1, and then we have another wall that is a temperature T2. And now let's consider this kind of thermocouple, one placed here. And then I got one there. Maybe I have to reduce, sorry for that. Yeah, then one other like this. And one other like that. And for example, this one. And then I can have, for example, here the green material could be something related to steel. The other one could be something related to Costantana. Okay, we have one thermocouple here, another one there, and another one there. So we have a total of 3 thermocouples. Okay, thermocouple number 1. Oh, maybe I can use a different color. Thermocouple number 1, thermocouple number 2, thermocouple number 3. Okay. Let's assume for a hypothesis that both T1 and T2 are constant. Okay, constant, of course, in space. That is, the space distribution along the wall is having the same temperature. Okay. What's happening is that the output tension, let me call that once again EU, could be viewed as the sum of this thermocouple, the output tension of each thermocouple itself. So the output tension here could be viewed as the sum from 1 to 3 of each output tension of the 3 thermocouples that we are having here, just because we are having sort of series thermocouple. So as a result, we can say that the series circuit thermocouple, that is the overall thermocouple in our analysis, 3 thermocouples are placed in a series sequence. Okay, so this total thermocouple composed by 3 is having a sensitivity, is the output tension is 3 times the output tension of each thermocouple. So we increase by factor 3 the sensitivity of the overall measuring circuit. Okay, so if we have n number of thermocouple, we increase by a factor n the overall sensitivity with respect to the sensitivity of each thermocouple. Okay, so the serial circuit thermocouple is increasing the overall sensitivity. Okay, and sorry, by a factor of n if n is the number of serial thermocouple. Okay, so generally speaking, the output tension is given you by the summation from I equal to 1 to n of the EUI. Okay, in case of a serious configuration like the one that I draw. Okay, now it's shown. Maybe a refresh needed. It's not changing anything. Okay, maybe. Okay. Okay. So serious configuration is telling me that the output is the sum of the output. We increase the sensitivity. How about the parallel configuration? Configuration of thermocouple and number of thermocouple that are put in a parallel configuration. Let me show you this example. For example, we are having one wall here at the temperature 1, another wall there at a temperature of T2. And a third wall, for example, there at temperature T3. T1, 2, 3 are all different temperature. How about if we consider this thermocouple configuration? Like this one. Okay. So what we got is that we are having three thermocouples. So for example, here we have thermocouple number 1, number 2, number 3, but they are organized so that they are in parallel with respect to the unknown measuring temperature, T1, T3. So every thermocouple is giving you the output that is relative to the wall, to the unknown temperature. So the overall temperature, the overall output tension is the average of everything. That is, the parallel thermocouple configuration is telling you the average of the temperature in which they are located. Okay? So parallel configuration is giving the average of tension, that is the average temperature. Okay? So you want to increase the sensitivity, go with the series configuration. You want to have an average temp value information, go to parallel configuration. For example, this is very useful when you are having, once again, with the jet engine case, hot temperature jet engine case, and therefore you can have information of the average radial temperature of the case. Okay, so you can put a number of these thermocouples, and then do that so that they are in parallel configuration. If you're doing that, the resulting output tension is the average one. Therefore, when you are repeating the same approach of the one that we already described, you will have information of the average temperature. Okay. Then other issue that we have to consider in real life is that if you are, for example, putting your hot junction in a place, in a part of the structure with unknown temperature like that, okay, and that is your temperature thermocouple like this, okay. If now you are doing, let's say, something of this, and if the wirings are in contact with each other, then this last constant contact is telling you what is the temperature of this last contact. So you completely miss the unknown temperature T, but you have the information, or let me call that T prime, that is the temperature of the closest short circuit point with respect to the measuring point. Okay, so your EU now is the output tension, okay, of T prime instead of the unknown T. So you have to be very, very careful in isolating all the cables, because if there is an accidental contact, then your measurement will be completely wrong. Okay? Having said that, now let's see what are the practical measuring configurations that you can see, generally speaking, in your real life. And the first one, we will see just this one, maybe, is the base circuit. Okay. The base circuit is very easy. It's the one that you are expecting, no more than that. That is, you are having your unknown temperature ball, for example, to which you put your cold junction. You use two material. Let's assume, for example, to have the if we still and the Costantana materials, and this will be part of your metering circuit like that, for which we are having let's say voltmeter like that is telling you what is the output tension corresponding to that configuration. Okay, please note that this output tension is considering the electrical terminals temperature as the cold temperature. Okay, so this one let me do that very okay. Okay, so that is the typical configuration. Your hot unknown temperature, hot junction unknown temperature is T, that is there on the left side, that is the wall temperature or something, for example. Okay, you have your thermocouple that is composed by a steel alloy and a Costantana, that enters the measuring circuit. It is just a voltmeter. Okay, we can write that here. Okay, and please remember that the cold temperature is the one of the terminals, electrical terminals. Okay, and therefore you have to take into account that. So you need to have information of such a electrical terminal's temperature. Okay, and therefore in order to do that, you can use, for example, some information concerning, let's say, the resistive base thermometer, thermistor. Okay, you can have information by using a different transducer. Okay, once you know that output tension, then you can refer to the tables as we already did in order to estimate the temperature. Okay, so your readings, let's assume that the output that you read is equal to 2.877 millivolts. That is the reading from the voltmeter. Then you have to add the standard potential. We refer to 0, that refers to 0 degrees. Okay, so if the electrical terminals are at 24 degrees Celsius, that means that E24 for the same thermocouple type is 0.952 millivolts. Okay, so the overall output potential is EU plus E24, this one, that is equal to 3.82829 millivolts, and from tables, you find out that the temperature is the same 90 degrees. Okay? That is just an additional exercise that you can have. But however, the general layout that we call the base circuit is the one that I just draw. Okay? So hot junction at the unknown temperature, thermocouple, and then electrical terminals. You need to have the information of the temperature of those electrical terminals because they will refer to the cold temperature. So you have to know what is the standard potential of the cold temperature, cold junction at that temperature, and then sum up everything. You have to use table, but just one table. Okay? And that is how we can use it. Time is over. Question from home, question from the classroom.
Yeah, real quick. What is the E24? What does that represent again?
Yeah, is there if the electrical terminals are at 24 degrees Celsius, okay, the output tension E24 is, for example, 0.952 millivolts.
Okay, so that's
So-
just the temperature.
Yeah, is
Okay.
the output tension referred to the 0 degree Celsius of a thermocouple, the same thermocouple with the hot junction at 24 degrees.
Okay.
24 degrees is the temperature of the electrical terminals. And of course, you need to know that temperature. In order to do that, you can use different transducers, resistive base, for example, or others. Okay.
Okay, thank you.
Any other question? Very good. So that is for today. See you Friday. Okay? See you on Friday. Bye bye all.